Lesson 2, Unit 6, using proportions to solve problems. Make sure you write some of these examples down. So if you look at the reciprocal property, basically what we're doing is we're swapping A and B's location. You're flip-flopping them. And then if you do that on one side, you also have to flip-flop on the other side of your equal sign. Otherwise, you wouldn't have an equal statement. So like we talked about last time, the geometric mean, we had a formula, A over X equals X over B, or in this case, it's A over B equals C over D. If you flip-flop these, you'll get the same answer. And again, why does that work? Because I want you to think about cross-multiplying. If I multiply B times C, that's going to equal the same thing as C times B, because the order of multiplication does not matter. And one other way I can always get an equal statement is if I just add something on the top, I better add that same thing on the bottom. So if I add, and again, notice that these values are the same as the denominator. So I'm adding the denominator right here, meaning I better add my denominator over here. So some equivalent proportions. Again, I could flip-flop. I could say 10 over 3 equals 4 over x. There's one. Maybe I compared my numerators to each other. I said 3 over x equals 10 over 4. And again, I can flip-flop that. X over 3 equals 4 over 10. Maybe I wanted to use that last property and I wanted to add 10. So I said 13 over 10 equals x plus 4 over 4. Because I added 10, which was my denominator, and I added 4, which was my denominator. All right, so if I look here, side MN is right here, side RS is over here. So I like to think about it as my long sides, my short sides. So it looks like this would be my long side and my long side. So we're kind of looking at long side over long side. And that's going to be compared to, if I look at my second letter, I have NP and ST. So I'm going to call that the short side. This is the short side and the short side. So, right, 4 true proportions. Well, if I wanted to stay long to long, I would say 8 over 10 equals 4 over x. Sure. Could flip-flop it. Okay, could always flip-flop it. So I'm going to say 10 over 8 equals x over 4. If I wanted to use the Pythagorean theorem, I could figure out the hypotenuse. I don't want to do that right now. So I'm just going to say, well, maybe I wanted to just look at the same triangles. So I want to look at MN over NP equals RS over ST. So that would be 8 over 4 equals 10 over x. And again, if I've got that, I could flip it. Or I could add my denominators. Find BA and BD. So BA goes all the way down, BD stops. But notice I've got a few triangles here, okay? I've got this triangle right here. I've got my big triangle. So what I'm going to try to do is I'm going to try to write down as much as I know, or I'm going to use what I know. And it looks like I know a lot about the hypotenuse. So I'm going to talk about it as my small triangle over my big triangle. And my small triangle is in orange, and my big triangle is in yellow. So if I'm going to look at this, I'm going to look at the hypotenuse. So I'm going to say small hypotenuse over big hypotenuse. And my small hypotenuse is 18. My big hypotenuse is going to be 18 plus 6 because I got to add this extra little section in here. And then I'm also going to compare that to whatever we want to call this other side, whether it's long side, whether it's short side. But I know on my small triangle, I have an X. And on my large triangle, I have X. But then I also have this section that's 3. So I'm going to call it X plus 3. So I'm going to use these two, set up an equation. 18 over 24 equals X over X plus 3. Cross multiply. 18 times X plus 3 equals 24X. 18X, 18 times 3 is 54. I'm going to get my X's together. 54 equals 6X divided by 6, and X equals 9. That doesn't answer the question though. The question asks for BA. So BA equals X plus 3. 9 plus 3 equals 12, which means BD is just X, which equals 9. A lot of work. Last example. You buy a 3D scale model of the Reunion Tower in Dallas, Texas. The actual building is 560 feet tall. Your model is 10 inches tall. The diameter of the dome on your scale is about 2.1 inches. What is the diameter of the actual dome? So again, I'm going to think the replica to the real life, or I'm going to think small to big here. So I'm going to say, okay, my small scale is, or my small model is 10 inches tall. But I know that the actual building is 560 feet. And then I know that the diameter of my dome is the small one is 2.1 inches, but I need to try to figure out what is this going to be in feet. So I'm going to cross multiply. And I know that when I do this, what's going to end up happening is I'm going to end up having inches divided by inches, and they're going to cancel out. So I'm just going to call this X. 10X equals 560 times 2.1, which is 1,176. And when I divide it by 10, I get X equals 117.6. And again, that answer is going to be feet. 117.6 feet. And about how many times as tall as your model is the actual building? So we'll just look at what we plugged in. We said it was something like, if the building is 560 feet and our model was 10 inches, I would say that it's hard to compare inches and feet. So we're going to say, well, let's get inches. So 560 times 12, because there's 12 inches in a foot, is going to give us 6,720 over 10. So I would say the model is about 672 times, or the real one is this much greater